I'm going to try and cover the top 10 in a really brief fashion for statistics.
Introduce yourself.
I was introduced in the last hour.
Well,
My name is Al Kinderman.
thank you.
I'm the chair of the Systems and Operations Management Department. And I take orders from the cameraman all the time.
That's true.
Okay, so I assume you've all seen your top 10. Some of you can have it with you. So the first thing is, we all know standard deviation, variance, mean, median, mode. Sure we do. Okay, so let's start with, let's find a mean. How do you find a mean? Add them up. You did bring your calculators, right?
No.
Hey, it's stat time. You better pull them out. So, find the mean. What do you have to do? It's finding the average, right? This is 4th grade, 5th grade, whatever. Anyway, so add them up. What do you get?
7.
How many numbers do we have? 5. So the mean is 7. And just in terms of symbols, the sample mean we write as X bar and a population mean. What's that thing called? Not that one. It's this one. Okay, right. So if this had been a population, remember, we would have written mu. But let's pretend for the moment that we're talking about a sample. So we write X bar. What's the median? So this is the mean. 6. Oh no, did I make that mistake? I hate doing that. Why is 6 the median?
In the middle position.
What's the median? What? Just because I wrote them in a different place, suddenly the median changed? Okay. Before you find the median, what do you have to do? Sort them. Put them in order. So the reason the cameraman was laughing and I was kicking myself silently was, by accident, I had put the 6 in the middle. And my whole point to the students is, no, don't just look at the numbers the way they're written down. You have to put them in order. 2, 5, 6, 10, 12. And so the median is the number in the middle. Half above and half below. What happens if you have an even number of numbers? Take the 2 middle ones and average them. Okay, so it's still the middle. How do we find a variance? This is where it all stops. We were going so great there for about 3 minutes, and then suddenly we all grind to a stop. Find the variance, you have to take the deviations from the mean. And I believe on this test, since we're teaching concepts here, and testing concepts rather, there aren't any really fancy numbers. They'd be simple numbers like this with nice round means and fairly easy to do. So what do we have? 2 minus 7, negative 5, 12 minus 7, plus 5, 5 minus 7, negative 2, 10 minus 7, plus 3, and 6 minus 7, negative 1. Your deviations, just as a check, should always add up to 0. 5. So the negatives are 5, 7, 8, and the positives are 5 and 3 is 8. Add up to 0. What's the next step in finding the variance?
Square.
Square all those. Square each one of those. So we get a 25, a 25, a 4, a 9, and a 1. Then what?
Multiply.
Add.
Just add them up.
Get the square root.
We're not finished yet. We're getting there. So what do you get?
64.
64. If this is a sample, how do you find the sample variance?
Square root.
No, there's no square root. Sounds nice because 8's easy to do, right? No, we have to do something first. The variance is the average square distance away from the mean.
Standard deviation.
We're not ready for that yet. Finding the variance. We
Listen.
found the distances away from the mean. We squared the distances away from the mean. But that's not what the variance is. The variance is the average squared distance away from the mean. You have to divide by something. We're doing it like an average thing. We divide by 5,
Minus 1.
or is this one of those tricky ones you divide? It's a sample, so we divide by
5 minus 1.
So, no,
5,
4.
35,
4.
7. Whoa, are we in big trouble? When is this test? I don't want to know anything about statistics, I just want to pass the test. So. Let's get serious here.
It's 5.
4.
4.
Definition of the variance for the sample variance is it's the sum of the deviations squared divided by n minus 1. Oh, I knew that all along, you know. Hey, I got this cold, you know.
do we have any formulas on the?
No, there are no formulas.
So we're supposed to remember this?
Absolutely.
Well, we'll see you guys next semester.
We're not free trials for the test, so.
The population variance, and that was that swinging finger somebody had earlier when I asked what the mean was. Okay, this is sigma, right? The population variance is you find deviations from the mean, but now square, add them up, but now we divide by,
5. I know that for sure.
Good.
you divide by the population size. So what's the difference? If it's a population, you divide by n. If it's a sample, you divide by n minus 1. So 64 divided by 4 is 16. Wow, that guy even didn't plan this? I'm just good. So what's the standard deviation? 4. Standard deviation is the square root of the variance. This is how you find the standard deviation. You don't start finding the standard deviation. You always find the variance first and then take the square root. Okay, so we've got a mean, a median, a variance. What's a mode? We don't really have one in this example. Because the mode is what?
Most frequent?
The number that shows up most frequently. So in this particular example, we really don't have one because all the numbers show up once. Okay. On the ideas of histograms, bar charts, box plots, the real issue is we're not going to ask you to draw one, but we're going to ask you to know when to use each type or possibly each method. So what's a histogram? And when do we use it? What's a histogram?
It includes the boundaries at the base. I believe.
Well, first of all, it is a graph, right, and it does something like, the key thing, though, is we use histograms for numerical data. So that means this could be family income. And we could divide incomes into a group of categories and then just take our sample of families and count how many had low incomes, lower middle, middle, and so on, whatever those groups were. How many units do you take? 1 to 3, 4 to 6. Can I do this? 7 to 9. I got stuck there for a minute. Right, so So this could be 1 to 3, and then 4 to 6, 7 to 9. But the key thing is numerical data. Something that looks similar but is distinguished by two features. One is when we draw it, we actually put a gap between the bars. And actually, often you'll see a bar chart if there aren't too many categories. Let's make it look like this. You often see them drawn horizontally as well. You almost never see a histogram drawn horizontally. Histograms always have the numerical data along the x-axis, and the heights represent the frequencies. These also represent frequencies, but what's the difference? Well, obviously, since I made the big point about for a histogram, we use histograms on numerical data, this has to be
Descriptive?
not descriptive. So something that's not numerical. What sort of data is not numerical?
Quantitative?
Does quantitative mean not numerical?
Qualitative.
Qualitative, thank you. Okay, because quantitative, quantities, numbers, you know, quantitative and numerical, those are the same thing. So it's qualitative, in particular, you can refer to it as nominal data or categorical data. What city do you live in? And then I get the answers from a bunch of students, and there's so many that live in one city, there's so many who live in the other. What's the appropriate chart to use for that? That's the bar chart. You don't have the cities all running together. Okay. So that's when we use a bar chart. Okay, let's just keep going. I don't think there's anything on box plots. I hope I'm right. Okay.
I think that's right.
We know your work.
That's right. I mean, you are taking a multiple choice test, so there are certain test taking techniques you can use. Like eliminate all the other answers and there's only one left, even if you don't know what it is.
Can we have our own calculator at the exam?
Do bring a calculator, yes. I don't know what the rules are this semester. Last semester, sometimes we made students use little cheap calculators we had, so students would bring in things that had all the formulas already saved inside this thing that looks like a handheld calculator, but really is like a supercomputer that has net access, so you can look everything up on the web while you're sitting there. So, who owns one? Okay, so, yeah, right, that's what I'm worried about. No, there's no formula sheet. Okay. That's why I'm here, to make sure you know the formula. Okay, so, topic 2, test a hypothesis. I have no idea what this is. One of the hardest things in doing tests is getting the hypotheses set up correctly. A researcher suspects so I'm talking about some population, and we're going to use this same data we just started with. A researcher suspects the mean is greater than 5. Perform a test. Is there evidence in that data that the mean is bigger than 5? Well, on the face of it is, because we got a mean of 7. But on the other hand, if the population mean is 5, when you take a sample, you're going to get 4 or 7 or 3 or 6 or who knows. You're not automatically going to get 5 as your sample mean. So the question is getting a sample mean really proof that the population mean isn't 5? Or is it just sort of naturally where you'd expect it? Well, before we get to that, the answer, we have to talk about how do you set up the null and the alternative hypotheses. Did you learn, depends on what class you took, some books write H sub A for the alternative. Are you used to using A or using 1?
1.
Okay, so 1, that's fine. What is the appropriate null hypothesis for this problem? Well, it obviously has something to do with the mean, and it has something to do with 5.
Greater
Is
than
it greater than 5?
No.
Equal to 5? Less than 5? Less than or equal to 5?
Greater.
Greater than 5. Okay, no. Because here's the rule. I'm going to teach you the rule. And this is the easy way to remember. If you're trying to prove something, that's always the alternative. So the researcher was suspecting that the mean was greater than 5. Do you have evidence that it's greater than 5? If you're looking for evidence of something being true, that is always the alternative. The other trick is the null hypothesis always has the equal sign in it. H sub 0, usually called H naught or H null, the null hypothesis, always has the equal sign in it. Now, if you want to write a less than or equal to or greater than or equal to, it's okay. I always teach students, just make sure you get the equal sign in there, because that's the key feature. So make sure your null hypothesis has the equal, and what you're interested in proving is the alternative. So if I wanted to put a less than or equal to or greater than or equal to, where would I put it? I wouldn't put greater than or equal to here, because then that'd be a conflict. I could put what here? Greater than or equal to? No, I've already got a greater than. This would have to be less than. See, it's so confusing. So what's the simple way out? Just write equal. Okay. Now, if the problem, since these are multiple choice, they'll say things like, the researcher suspects the mean is greater than 5. What's the right hypotheses? And they'll have equal versus greater, less than versus greater, less than versus equal to, greater than versus equal to. They may have in there less than or equal to versus greater than. If there were no other choice, if this was less than or equal to and this is greater than, this would be the right answer. So remember, when you actually see it, it's not going to be just sitting there. It's going to be a choice out of several. So as we go along, much faster than I'm going right now, I'll start giving you typical wrong choices. They're the ones you would usually choose, right? Yes?
Real quick, so you said you test for the alternative then, is that correct? When you know
If
the
you're trying
outcome?
to prove something, typically, unless you're trying to prove two things are equal, but usually that's not what you're trying to do. You're trying to show women make less than men. You're trying to show, I don't know what. But usually what you're trying to show is that there's a difference or something is not equal to something. Okay, so how do we do this? Well, the point is, obviously, we have to sample, and we're going to reject H naught if X bar is far above, far below, or far away from in either direction from 5. Looking at this particular problem, what is going to be evidence to cause us to reject H naught? Far below, far above, or far away from in either direction?
To reject H naught.
To reject H naught. Rejecting H naught means what? Rejecting H naught means what do we believe? No, well, it's not. This is a lesson for anything mathematical you do. It is never a good word. Because I don't know if it means the population mean, or it is the sample mean, or it is the standard deviation. So let's try and communicate clearly. we're trying to test whether the population mean is 5 or the population mean is greater than 5. What would be evidence to make us believe the population mean is greater than 5? It would be if our sample mean is far above 5. So rejecting H0 means we've got the evidence we're looking for. The researcher is right. There really is proof that what? The population mean is greater than 5. So, there are two versions of this problem. This is not the version we actually have here. But if we actually were given a problem where they told us what the standard deviation is, how do we know whether 7 is far above 5? If H0 is true, then the mean of x bar should be 5. And we're going to reject H0, what did we say, if we were far above 5? Oh, that's right, there's this other thing. What's this alpha thing? It's got something to do with testing. Alpha is the probability we reject H0 when what's true?
When it is true.
Did you hear that bad word? Did you hear that bad word? When what is true?
I can't help it.
When which one is true? Alpha is the probability we reject H0 when? No. When H0 is true. Because alpha is the probability of making a mistake. It's a particular type of mistake called a type 1 error. So if you reject H0, remember, what does rejecting H0 mean? It means you believe H1. Well, if you reject H0 when H1 is true, that's not a mistake. You're doing the right thing. The error is to reject H0 and say, no, it's not 5, when in fact I said the bad word. When the population mean really is 5. Okay. So the type 1 error is to reject H0 when H0 is actually true. What's the type 2 error? That's almost as bad as it. Right, it's the other way around. Now say the other way around.
To accept when it's not, when
It's the probability of accepting, which one?
The right answer, I mean,
Okay, you were trying. Accepting which one? One error you just said is to reject H0 when H0 is really true. So the other error is to
accept when it's not, when it's false.
Very good.
right, or H1 is true. So the probability of accepting so type 2 error is accepting H0 when H0 really is false. Type 1 error is to reject H0 when H0 really is true. In a typical problem, you're told what alpha is. So let's say we're told that alpha is 0.05. What do I make of the fact that I took a sample of 5 and got an x bar of 7? Suppose sigma is actually known. Suppose we know, I'll just do this. Suppose we know that sigma equals 3. How do we decide whether we should reject H0 or not? Well, there are actually two methods. One is to actually figure out what this number is that divides who's close from who's far, where we should accept H0, where we should reject H0. The shaded area is where we're rejecting H0, because that's where we're far away from 5, right, far above 5. The other method is standardize first. Standardized means to do what? Take x bar minus the claimed mean divided by the standard deviation of x bar, which is sigma over the square root of n. What do we call that thing?
C-test?
Well, this actually is z. Right. So to standardize means figure out how many standard deviations away from the mean we are. So in this case, we would do 7 minus 5 divided by 3 over the square root of 5. Did somebody do that for me quickly? So it's 2 divided by 3 over the square root of 5. About 1.7. But sometimes I guess well, sometimes
1.5.
I...
1.5.
Exactly?
1.4907.
What was that?
1.4907.
Root of 5 is that close to 1.23? I mean 2.1. Okay. What is 2.23? Did you get 1.5 for the whole thing?
Yeah.
Okay, so it's 1.5. Our decision rule that we were going to reject h naught if x bar was far above 5 has become the new rule, which is reject h naught if z is far above 0. As if we basically draw the same picture, but draw it in terms of z, what we're saying is we should reject h naught if the z we got. If 1.5 is actually in here, then what should we do? Except in here, except which one? H naught. If we end up with, if z equals 1.5 is really out here, then we should reject H naught. Right. So if we're in here, we're saying, that's not so different. The population mean is really 5. We have no proof that it's not. If we get a z that's out here, we say, whoa, that's really far away. And therefore, that's evidence that the population mean is greater than 5. 7's really far above 5. So that's what we've done. We've changed the question to 7 close to 5 or 7 far above 5 to is z equals 1.5 basically a small number, not so many standard deviations, or is z equals 1.5 a lot of standard deviations. Now, ordinarily, if you were doing this yourself, you would have to look at a standard normal table, look up the right z that goes with this being 0.05. There's a special notation for that. It's called z with a little 0.05 down below, means that's the number that has 5% of the area to the right. Okay, here's what a sample test question would look like. Well, I'll stop there. There's 3 good answers. What's the correct answer? Well, if the problem was set up and told you that sigma was known, then what do you do right away? Disregard t. Even though I haven't gotten to t yet, t is when sigma is unknown. So we know it's got to be one of the z's, so which one is it? Okay. Where's 1.5? If I tell you that z.05 is 1.645, where's 1.5 on our picture? Closer to 0 or out in the shaded area? That's where. So what am I supposed to do again? Accept h0 because the z that I got is less than the cutoff point. This is the way typical questions on the exam will be phrased. There's another way of doing it, but they're not going to make you look up in a table. They're basically going to tell you here's the value out of the table. But they might do something like this, like use 2 different tables, say, so at the same time they're testing, should you be using t or z? Oh, z, is it, what's the right decision because it's less than? Should I reject h0 because it's less than, or should I accept h0 because it's less than? The correct answer is accept h0. Well, sigma's unknown, and what do you use? You use t, it's x bar minus mu divided by s over the square root of n. And I mentioned it just briefly minutes ago. With t, you have to be familiar with the concept of degrees of freedom. In our example, how many degrees of freedom do we have? I heard an answer out there. What did you say? Did somebody say 4? Why is it 4? Because it's n minus 1. This, in fact, is exactly the same n minus 1 that when you find the sample variance, you divide by n minus 1. So you just have to remember that. So again, a problem might say, what's this? 1.3, 1.2.
$1.12.
So over here, when I write down the right answers, or rather I write down the wrong answers, I want you to understand we were very clever at coming up with really good wrong answers. So possible wrong answers are reject when you're really supposed to accept. The other is comparing to a z when you really should be comparing to a t. Comparing to a t with 4 degrees of freedom, but then I can also have compare it to a t with 5 degrees of freedom. Which one's going to be the right answer without knowing anything else? It's not the z, it's not the 5 degrees of freedom. It's compared to the t with the 4 degrees of freedom. And then you have to look, is it the accept or reject, which is the right one. But again, the types of comparisons we're making is, again, if we were doing 0.05 all on one side, we'd be looking at a t with 4 degrees of freedom. I'm just making up these numbers. I don't have a t-table in my head. So I'm not saying this is the right number, but some number like that would be given to you. It would just be given to you, and where's 1.12? Inside. So again, the right answer here would be and I'm supposed to do the top 10 in 1 hour. Okay, I'm spending a lot of time on testing because I know from experience, both in my own classes and on this test last semester, that was one area where students had a lot of problems. Okay. The other thing is, just really briefly, if I am testing the mean is 20 versus the alternative is not equal to 20, what changes in what I was doing? Well, now I'm going to reject either direction, right? If I'm testing equals versus not equal to, then I'm going to reject if I'm far above or if I'm far below. Because this says, I don't know if the mean is 20 or whether it's bigger than 20 or whether it's less than 20. And so if I get an X bar that's far below 20, then I say, yeah, the population mean is at 20. Or if I got an X bar that was far above 20, I would say, yes, that's evidence the population mean is not 20. The trick here is, if you know alpha is a value of 0.05, what do you do in your picture?
That's one side.
Wait, you're looking at this picture and you say, this is two-sided. That's why I shaded both sides. So how much area is on each side? 0.025. You have to split your alpha in half, right? Because there's a 5% chance of rejecting. Half of it's on the left, half of it's on the right. So it's 2.5 and 2.5. So one of the things we would do here is writing down the possible answers, we'd say, well, one of them would have the T.05 in it, and the other would have the T.025 in it. And which one's the right one to look at? Right. T.05 is obviously going to be a wrong answer for this problem. So you have to be aware of two-tailed versus one-tailed, two-sided versus one-sided. So let's move on and talk about confidence interval. By now, we should be really good. This is going to go quickly. I want you to find the confidence interval or the population mean. Same issues. Sigma's known. We're going to use Z. Sigma's unknown. We're going to use T. Let me do a 95% confidence interval. If I tell you that X bar is 26, N is 18, and we know the standard deviation is 8. Confidence interval is X bar plus or minus. It always has a plus or minus. Why? Because we're making a single guess and saying, I know the guess isn't right, so I want to expand and make an interval. And say, I think the population mean is in that interval. I'm going to go plus or minus Z times the standard deviation of X bar. The standard deviation of X bar is always sigma over the square root of n, just as we used in the testing. So in this case, it would just be 26 plus or minus. You would have to get the Z value out of the table, 8 over the square root of 18. Well, I shouldn't even have told you that. Here's a test question. They tell you the mean is 18, the average is 26, the standard deviation of the population is 8. Find the confidence interval. They wouldn't even show you this, and they would show you 4 possible answers. Is it 26 plus or minus T.05 times 8 over the square root of n? 26 plus or minus Z.025 times 8 over the square root of n? 26 plus or minus Z.05 times 8 over the square root of n? Or T.025 times 8 over the square root of n? Which is the correct answer? I highly recommend drawing pictures. Confidence intervals are always two-sided. If we've got 95% in the middle, how much is in either side? 0.025. So therefore, it's not t.05 and it's not z.05. So then the only question is, was sigma known or sigma unknown? If sigma was known, the right answer is, that's the correct answer. So that's the way the question is going to be phrased. So you're expected to know, should I use 0.025 or 0.05? And is it z or is it t? When do we use t? Then it looks exactly the same. It's x bar plus or minus t times s over the square root. Now, the trick, the hard part for most students is not this, it's reading the words. And so now I'm going to read some words to you. Yes?
I have a question. Don't we use z when it's 31 or more and t when it's 30 or less?
I think you're safe with that. Some people teach that. Others teach the way I teach it. What happens is, even if sigma is unknown, as n gets large and the degrees of freedom gets large, t starts getting very close to z anyway. So a lot of teachers just teach, well, once you get up to a certain level for n, t and z, nah, it really doesn't matter. Z is easier. Let's just go ahead and use z. But of course, actually, if you're using a computer, for example, it doesn't matter. So even if n's 400, it can do a t with 399 degrees of freedom. So I think you're okay with that, but you're really okay with this.
Okay.
Okay. Oh, about the words. Okay. The prices of cell phones have a standard deviation of $30. A sample of 20 cell phones had an average price of $134. You expect me to remember it now? Who's been writing quickly? Read it back.
The standard deviation.
Right. The prices, the numbers aren't so important. Okay. So the prices of cell phones have a standard deviation of $30. A sample of cell phones had an average price of $134. The only thing I want to know is, did I tell you sigma or did I tell you s?
Yes. You said sample.
I said sample. Okay, here's the trick. I did say sample somewhere in there. But did I say sample in close proximity to the word standard deviation? I said cell phone prices have a standard deviation. But which cell phone prices are those? That's all the cell phone prices. That's the population of cell phones. I just told you sigma. Cell phones, all of them, but you don't see the word all of them. Cell phones have a standard deviation of 30. That is sigma. That is the population standard deviation. The next sentence then said, I took a sample and found a mean of something. What mean is that? Is that x bar or mu? That's x bar. Why? Because I said I took a sample and found a mean of $134. So the words I said, I actually told you first that sigma was 30, and then I told you that x bar was 134. How would those words have been different if I wanted to tell you s? The words would have been, in a study of cell phone prices, a researcher took a sample of 20 cell phones and found a mean of 134, and a standard deviation of 30. What did I just tell you? I said I'm studying cell phone prices. Then I said I took a sample and the mean was 134 and the standard deviation was 30.
The standard.
I told you I took a sample. And following the word I took a sample, it said the mean was 134 and the standard deviation was 30. So if the word sample comes before the word mean and standard deviation, then I've just told you the sample mean and the sample standard deviation. What was different about the other words? I just said cell phone. By implication, when I'm saying cell phones, I'm talking about all cell phones. And after I told you the standard deviation, I said, oh, and by the way, I took a sample and found a mean. So what's the difference in the wording between the two? In this case, I said I took a sample and found a mean and a standard deviation. So I've just given you what? X bar and S. Here I said cell phones have a standard deviation. Which cell phones are those? Just my sample? No, that's all cell phones, meaning this is a population standard deviation, meaning I just told you sigma. I then took a sample and got a mean of 134. So that's key, whether it's testing hypotheses or confidence intervals.
Just paying attention to the word sample in the sentence. If
It's
going,
very important.
Right, okay.
Right. But when the words say the standard deviation is, was that within the context, I took a sample and the standard deviation is? Well, it might be. So if the words say I took a sample and the standard deviation was, then you're being told S. If the words just say cell phone prices have a standard deviation of, that's sigma. So that's one thing you've got to be very careful about. And in the next 5 minutes. Well, in a sense, we've already done 9, because 9 is what's the distinction between a population and a sample? A population is all the items you're interested in. A sample is just a part of it. Right, okay. Let me skip over regression for just a second and go on to expected value. If I tell you, here are a bunch of possible values, 0, 1, and 2, and the probabilities, there's a 30% chance I get a 0, a 20% chance I get a 1, and a 50% chance I get a 2. How do I find the mean or the expected value of this distribution?
Times X by the probability?
Right, you don't just add up 0, 1, and 2 and divide by 3 and get 1. Because the numbers say that I get more zeros than ones, 30% to 20%, and I get a lot more 2s. Half the time I'm going to get a 2. So we take x times p of x, 0 times 0.3, 1 times 0.2, 2 times 0.5, which is 1, and then you add. And you don't divide by anything. That's the expected value. The average of these numbers, in a sense, is 1.2. It's not 1. Why was the mean greater than 1? I mean, I see 0, 1, and 2. Isn't 1 right in the middle? Why was the mean 1.2? I told you the reason about a minute ago. Because you get 2s more often than anything else. So just relative to 1, you get 2 50% of the time, you get 0 only 30% of the time. So balancing around 1, you get more 2s, less zeros. So the real average actually is not 1, it's more than 1. It turns out to be 1.2. So just make sure you know how to compute an expected value that way. Then there are a few other basic ideas. If I were to add 10 to all those numbers, what would that do to the expected value? If I did the same problem over again with 10, 11, and 12, can you tell me what the expected value is without doing any work? Not 12. 11.2. Right? Because I just added 10 to all the numbers. So now I'll have 10, 11, and 12, and I'll have more 12s than 10, so the average isn't 11, it's 11.2. So adding 10 to all the numbers just makes the average go up by 10. What would happen if I doubled all those numbers? If I did it with 0, 2, and 4? Can you tell me what the expected value is without doing any work? Good. The expected value is going to be double. If you double all the numbers, the average of those will be twice as big. Okay, good. Took care of that one quick. 4 minutes for the next 4 top 10. Hey, that last one was real quick. That's good. I'm proud of it. Okay. Number 4 says calculate a regression equation and make a proper interpretation. The truth is, on the test, you are not asked to calculate a regression equation. You are asked to interpret the coefficients. What was the name of the jewelry store or manufacturer an hour ago? You didn't have a name? No. Okay. So it's J&R Jewelry, and I'm going to do J&R Jewelry sales and production costs for the last 12 months. So when sales were 5,000, costs were 1,243,000, and whatever. There's a whole bunch of numbers here. Okay? The idea of a regression is, well, what are the issues we have to think about? So in a sense, I just gave away the answer is who's X and who's Y. X is called the independent variable, Y is the dependent variable. And that's what you got to think about. Do your costs depend on, well, we're assuming we produced the order, like in the last example. So they're producing whatever their orders are for that month. Are sales a function of their costs, or are costs a function of their sales? Cost should be depend on, even if it's not a strict function, that's the right way to think about it. So who's the independent variable? Sales or production. What's the dependent variable? How much it costs to do that. Right. And what you're going to end up with is not a nice, neat thing where it's always the same the way those accountants want you to believe, but you're going to end up with a whole scattering of different levels of sales. You're going to have different costs for that month. But the idea of a regression line is we can use a formula, and again, you're not going to be asked to use that formula, but you're going to be given a line, and you're going to be asked to understand what that line means. And let's see if I can do this right. And suppose you get the equation y equals $850,000 plus $195X. What does that mean? What is the meaning of the 195? It's the slope of the line, so that says for every increase in Y increases by 195. The only problem is, the question is going to ask you about the sales of the necklaces and the costs. So say that same thing again, but say it in terms of necklaces and costs of production. For every extra necklace produced, your costs go up by, see, I was listening during the last hour. It was 190. Well, I had to change it a little bit. Okay. What's the meaning of the 850,000? That's your fixed cost, because that's the y-intercept, which means even if x were, what's the meaning of the y-intercept? It's the value of y when x equals 0. So even if x equals 0, you would still be spending $850,000. One thing you have to be careful about oftentimes you'll see problems that are like this. It's sales in thousands and costs in millions. Oh, I'm in big trouble. Tell me the meaning of this equation. I think I even did it right, which was the scary part. Every time sales go up, how much do sales go up? 1,000. Right, so now it's not over here, it was sales went up by one necklace. Here, when x changes by 1, it's actually 1,000. Every time sales go up by 1,000, costs go up by, not 85, over here. Slow. 0.195. So sales increase 1,000 necklaces. Costs go up by how much? 0.195 what? That's what I said. Did I actually do that right? Right, because if costs went up by, over here, costs went up by 1,000 necklaces, that would be how much more money in cost? 195 times the 1,000, 195,000. 195,000 expressed in millions is how many millions? 0.195 million. So this actually is exactly the same equation as that. The fixed cost is what? 0.85 what? Millions of dollars. Right. So this is still, because the y's are in millions. So this is 0.85. This is the value of y when x equals 0. So this is 0.85 million. So the problem could do something like that. So you have to be able to use units and understand what the units mean. I know, we're over time. What else do we know? Confidence interval, regression equation, test of hypothesis, expected value, population and sample. Okay, the one I really want to talk about is, just real quickly, well, we already did normal versus t. The only thing really in here that's key is the binomial. What's the binomial distribution? How do you know you're supposed to use it? And what are its properties? In 2 minutes or less. Well, we have two outcomes when? There's something else that comes before the two outcomes. Well, those are the two outcomes. But those are a result of what? Are you going to pass the stat exam? Are you going to pass the stat exam?
No. Yeah.
Are you going to pass the stat exam? Well, actually, I don't think so was one of the possible choices. What were you supposed to say?
Yes.
Yes or no? Okay, so but what was I doing?
Sample.
Well, it's a sample, but it's also called trials. It's like you flip a coin, then you do it again. So I asked one person a yes/no question. I asked a second person. So the binomial has trials. Each trial has two outcomes, success or failure. There's a probability of success. Apparently not very high. Okay. So the key thing is you have trials. You have two possible outcomes at each trial. The other thing is trials are independent. If she passes the exam, is that going to help you at all? If she doesn't pass the exam, is that going to hurt you? Right, your performance is independent of hers, so whether she passes or not has nothing to do with you. There isn't a curve. It's called get 8 right. Okay, right. So it's independent trials, successes and failures, the same probability of success. Not that you individually, but in picking somebody at random, if I know that 65% of the students pass, then if I just pick one of you, what's the chance you're one of the passing students? 0.65. Okay, so it's going to be the same. And the random variable is how many people pass. So we use the binomial when we're counting the number of successes out of n trials. So part of it is recognizing that when you should use a binomial, when you've got this thing like trials. Well, I'd asked Professor Cruz not to have me go last because I knew it would take more than an hour. I wanted an excuse to stop. I have another professor saying that. Right. So let me end there. If you've got a question or two, I do have time. If you want to go home.